Hi, in this example, we will do a timing analysis of a simple circuit and given some input conditions. Okay. Then, with the timing analysis, we may check if the circuit presents any hazards, any transient value at the output that is not expected or does not correspond with the function that the circuit does. We also see how to redesign the circuit to avoid the presence of hazards. This is something that is not one of the main skills in this course. I mean, I will not ask for circuit redesigning for avoiding hazards in an exam, but it's something that is interesting to see. So that's why I'll show you it in this example. And then we will obtain the chronogram of the new circuit to actually check that there are no hazards in the new version. So to analyze that circuit, we do it as in the previous example. Okay, we know that B and C are equal to 1. Okay, so these values are fixed. We obtain the equations of every output of a gate. Y is A and B. X is A complemented. Z, I don't make substitutions here, okay? It's very important to do a correct timing analysis. So Z is X and C. Okay, I do not substitute anything because if I do, I miss the information that Z changes when X changes, okay? Not when A changes. And finally, F will be the OR of Y or Z, okay? But in my particular case, B is equal to 1 and C is equal to 1, so these are constants, so my expressions can be simplified, okay? Y will be equal to A, X is the same, will be A complemented, Z will be equal to X, okay, because C is equal to 1, and F doesn't change, Y or Z, okay? So I will use this set of equations for every gate in my circuit to calculate my diagram. So the problem says that B and C are constant and A changes periodically. Okay, it's like if I want to test my circuit, probably the first option in testing a real circuit is to put a square signal in A, and square signal generated by a signal generator that is a signal that changes periodically, okay, from 1 to 0. So it's very common to use a signal like that. So A, will be a signal that changes something like this. It starts being 0. Change to line mode first. It starts to be 0 for some time, then it changes to 1. I will make it approximately square, okay? Then it changes to 0, stays 0 for some time, then it changes to 1 again, and so on and so forth. Okay? Now I can start analyzing my circuit. I can calculate the intermediate signals. For example, next I will calculate Y. Here I will calculate Y. Okay, after Y I could calculate X. Here, after that I can calculate Z, or I'll keep the order and calculate X first, then Y here, then Z here, and finally f here. So great, I'll consider the same delay for all the signals. That is a constant value, we may call it delta. So also we'll copy the information here. X is a complemented, Y is equal to A. Okay, being equal doesn't mean that it changes at the same time. It changes with the same value of A, but after some delay, okay? And Z is equal to X, and F finally is Y plus Z. So now I'm ready to draw my circuit. So X I calculate from A, so and Y also. So I will make some signals here, some references at the points that when A changes its value. Now X is the complement, so X start being 1, and when A changes to 1, it will change to 0 after some delay. I'll take just 1 square in my paper to represent that small delay. So it will change to the opposite value anytime A changes, okay? Actually, at the beginning of my representation, I don't really know what's the value of X before this point, because A is 0, so I'm sure X will be 1 here, but I don't know what's the value of X before. So I mark this in this way or with gray color or something to signal that I don't really know what's the value in this area. Okay, Y is pretty much the same, it's equal to A, but we'll take the value with a delay. So A is 0, so it'll start being 0. Now it is the same value, but it will change also with a delay with respect to A. Changes with a delay, changes with a delay, and that's it. And the same thing happened here. I won't really know the value of a Y up to a delta after the starting point. Oh, I draw that at the wrong place, sorry. So it's here, great. Now Z is equal to X. I'll draw the references for X. X takes its first known value here, and X changes at this point. Okay, it also changes at this point, also at this point. And Z is the same than X, okay? When it's 1, Z is 1, but it's 1 only after a delay. So I know it's 1 starting at this point. And then it will change with X. Same value, but delayed a little bit. And again, this is an unknown area for me. Okay. Now I'm ready to calculate F. F it's Y or Z. Y or Z. My reference points will be anytime Y changes, anytime Z changes. Y changes here, Z changes here. Y changes here, Z changes here. Y changes here, Z changes here. So I'm ready to make the calculations. Here you see we have Y0, Z, I don't know the value. So if it's an OR, 0 or unknown is unknown as well. It depends on this value. So up to this point, actually, I don't know what's the value of F. And here I have 0, 1, 0, 1 will make a 1. So starting here, I know f is a 1, okay? Before that point, I don't really know what's the value of f. And now I re-evaluate. Now it's 1, 1. 1, 1 makes a 1, so it will continue being a 1. Now it's 1, 0. 1, 0 is 1 with the operation, so it will continue to be 1 to the next reference. Now it's 0, 0. 0, 0 will make a change to 0, but the change will take place with the delta delay. But at the point it changes, then I have a new value, 0, 1. 0, 1 will make a 1 and will be applied with some delay. It will continue being a 1 here. Now it's 1, 1. It's also 1. Now it's a 1, 0. It's also 1. Look that this change here is the same that this change here, right? Because it is periodic. This is the rising edge here, which is equivalent to this rising edge here. And the falling edge here, it makes these changes. Okay, so we have f, and the problem says if the output presents any hazards. Oh, I see that the output is 1 most of the time, and it's 0 for some short time here. So I suspect this is a hazard, but how can I actually determine that this is really a hazard? I have to compare the value obtained in the chronogram with the expected value of f, okay? So let's see what's the equation for f if we analyze. So if we analyze f, we find that doing the functional analysis, that f is equal to y plus z, okay? In these conditions, when b and c are equal to 1, okay? So I make the substitutions. Y is a, and z is x. But in turn, x is a complemented, okay? So it's a plus a complemented. And this makes 1. So functionally, the value that f should take under my conditions, okay, is always 1, no matter if a is 1 or if a is 0, okay? This is the value I expect from my output, the functional value. So that's why it's 1 most of the time, but it's 0 in the short time. Why is it 0? Because it has a hazard. This is a transient value. During these changes, z becomes 0 for a short time until it gets its final value, that is a 1. The reason it changes to 0 is because when a changes from 1 to 0, this is 1, then the complement is 0. When a changes from 1 to 0, this changes from 0 to 1. But the change to 0 takes place before this change to 1. So during a small portion of time, both terms, okay, that are with y and z are 0. And while both terms are 0 here, during this short interval, it will make f to be 0 for a short interval until this term changes to 1 again, okay? Which is what we already know about hazards, okay? So that's the main part of the problem. Now, the point is that hazards may be avoided. How can we do to avoid those hazards? To avoid that, we need to check the easiest way is to check if these conditions can happen in any other change of the input. It means if I have a term that becomes 0 at the same time that the term becomes 1, okay? If I can change from two conditions that give the same final result, but one term, another term may change at the same time. So hazards happen because of that, because two terms giving the result, they change at the same time. The final result is the same, but in the middle, one term changes before the other. To see that, the easiest way is to, in simple circuits, is to take a look at the Carnot map. For that, we need the full expression of f here. Okay, let's calculate the full expression. Will be something like this. Will be let's make again some room here. Okay, great. And that's it. Let's move it here a little bit. Okay. Now, this will be just functional analysis. This is A complemented. This is A and B. This is A complemented and C. So finally, F, as implemented by that circuit, is this expression, is AB plus A complemented C. Okay. So this is the expression that corresponds exactly to this circuit. Okay, we'll move this expression here. And now we will obtain the Carnot map for this expression. So we better cut this and we'll add a new page. Okay, so we start a new page. So we have a circuit corresponding to this expression, and this represents a hazard. Let's take a look at the Carnot map. This is a 3 variables Carnot map, which is something like this. Here we have A, B, C. This is F. And my terms are AB, which is AB, A1, B1. Okay, this is my function has this term here. This is the AND gate, one AND gate doing this operation here. Okay, that corresponds with this AND gate here. Then I have A complemented C. A complemented C is A is 0, C is 1. So it corresponds to these two ones here. And this term is this term here. This term is done by the other AND gate, A complemented C. Okay. So the problem of the hazard is that we may change from when we are here in this place or this place, this term is making F to be 1. When we are here or here, is this term, let's draw the lines, is this term which makes the F to be 1. The problem is when we change from here to here. If we change inputs, from this place to this place, it means when I change A from 0 to 1 or 1 to 0, okay, like in our example, F is 1, but due to different terms. This is the risk of a hazard. When we change from here to here, it may happen that this term deactivates is 0 before this term is 1, or the other way around. Okay, that's why we have the possibility of hazards. So in the Carnot map, I can simply look for adjacent ones that are not covered by a common term. Okay, in any Carnot map, I can find these conditions. In this map, the only condition that may lead to one hazard is this transition here, from this place to this place. Okay, because if we change from here to here, there are two inputs changing. It's not a problem actually, because we are looking for a static hazard. Static hazard happen when there's only one input changing. So how can we solve it? It's actually very easy, because we need a term that will be 1 whenever we are here or here. We will never have a hazard changing from here to here or from here to here, because the term will, this term will be 1 in both cases. So it's enough to add a new term that I put in a different color. If we add a new term to my function, okay, then when A changes from 0 to 1 and B and C are 1, there will be no problem. This term may become 0, this term may become 1, but in the middle, this term will ensure that F is 1 all the time, eliminating the hazard, hopefully. So it will be enough to redesign F with the following, with a circuit based in the following expression. I will still have AB. I will still have this other term, a complemented C, but I will add this term in the middle, which is BC. Okay, same function. Now, to check that we have no hazards, we will have to do the same thing. Let's consider the same case. B equal to C equal to 1. So in that case, F when B is equal to C equal to 1 will be A plus A complemented plus 1. Okay, so I expect F to be 1 all the time. And now to check the result, we should do the analysis of a circuit like this. Okay, my circuit will be something like an AND gate, another AND gate, and another AND gate, followed by a NOR gate. The first gate has here A and B. Then we have A complemented and C. And then we have B and C. Okay, this is F. So to check that we don't have hazards, we have to check the same conditions. Okay, we should name the variables here. I will call this X. This will be called Y. I will call this one Z. We may call this one W. Okay, and then do all the calculations. Y will be AB, that in my particular case will be simply A, okay, because B and C are equal to 1. Okay, X will be A complemented, Z will be X see that in my particular case will be simply X. W could be BC. That in my particular case will always be 1. So now that I have the expressions for all the intermediate signals, I can do the timing analysis of the circuit. Okay, but you can see, you can do the complete timing analysis, but it's easy to see that if I analyze my circuit now, I will have A, and we'll have to analyze Y, Z, but we also have to analyze W is equal to 1 all the time. Okay, we don't need to put it here, okay, or we can put it here if we wish, and F here. Now A changes periodically like before, from 1 to 0, from 0 to 1, and so on. Now Y is actually the same than we had before. Z is exactly the same we had before. X that we need to put here, let's make room for X. We need to put X here. Okay. These all will be exactly the same actually. They have the same expression as before, X, Y, and Z, and so on. But they are not really needed because we can see that W will always be 1. Okay, and F is equal to here, see, F is equal to Y plus Z plus W. Okay, because W is always equal to 1, it will always be equal to 1. If you draw in the chronogram, we will say Y and Z may change however they want to change, but OR, making the OR with W, and W is always 1, will make F to be 1 all the time. Okay, so even without calculating the signals in the middle, we see now that F is always 1. We don't have the hazard anymore. The hazard that happened when A changed from 1 to 0. Okay. As I say, we can do all the analysis exactly the same, but at this point, we will arrive that we don't have the hazard because we are assuring now that this gate is making a permanent one here, a fixed one here in the problematic position. So I think we with this we finish the example. Thank you.